Cool. Well, if you don't mind, since we are recording, I'm going to go ahead and go through the notes that I posted in the stand-up. That way, anyone who might want. Oh, good. Vitalik's joined as well. Hey, Vitalik.
Oh, hi, Greg.
Hi.
Cool. Wow, there's two of us. I was telling Jack I was going to begin by going through the notes I posted in the stand-up. I probably do that in about 10 minutes or so, and that way, anyone who want, it's kind of an extra help to get through the notes if they're too terse or not as understandable in note form. So let me hit screen share, and I'll just do that. There we go. Screen share. Look. And here's that. Okay, cool. All right. And can everybody see that?
Yep.
Awesome. Okay.
There it is, yes.
Okay, cool. All right. So essentially, what I'll be talking about is a way to kind of derive the maximum number of pieces of the architecture formally, given a lot of the desiderata that we've been exploring over the last few months. So what I'm trying to do is to make sure that every piece that I possibly can, I can automatically derive from some data. And so I began with kind of the standard architecture of a modern runtime in kind of cartoon or abstract form. For a lot of folks who are concerned with correctness, you begin with a calculus that represents the model of computation most closely suited to your domain. And from that domain calculus, you can specify a type system. So that means that we're kind of here. And then you can project out to the user in terms of a user-level surface language and a corresponding surface type system. So the user interacts with this, and then you reverse path through a compiler to your core domain calculus, which in the actual compiler pipeline you can think of as a kind of intermediate representation. And then it turns out that you can derive an abstract machine in most cases from such a domain calculus. And then from the abstract machine you can actually derive a virtual machine. What the consequences then are that you have a correct by construction compiler pipeline. So to see what this looks like in a couple of modern architectures, if you talk to Simon Peyton Jones, the guy who invented Haskell, System F is the domain calculus from which he began, and Haskell is the surface language, and then the spineless tagless G machine, which is their virtual machine, is their VM. And there were some steps to get from here to here, but I've just kind of notated it as identity here. And also, since Haskell's been around for a long time, a lot of these components have, once they were kind of built out, have evolved separately. So it's a little harder to see this architecture directly, but it was initially there. One that's a little easier to see now is that after 8 years of use of Scala in the industry, they are redesigning this Scala compiler pipeline exactly along these lines. So there's a new calculus that has been under development for a few years called the dot calculus, and this has been helpful in improving the soundness of the Scala type system. And so the compiler, so there's a new compiler called Dotty, which takes Scala to a dot-based IR, and then the vestiges of the abstract machine are in the Scala compiler pipeline, and the final VM is the Java VM in this case. So that's a little bit more that's a little bit more modern use. And again, the important point in all of this is that their methodology exactly matches the implicit methodology here. Begin with a kind of boiled down, distilled notion of computation that can be represented as a calculus, and then work outward from that in a disciplined way to produce the components that get you out to the metal or as close to the metal as you want.
Okay. So question.
Yeah.
You said that the abstract machine and the VM and could be derived from each other, and the domain calculus in some ordered fashion, I guess.
Yeah, I'm about to go through exactly those points directly. But,
okay.
Yeah.
Just let me see if I'm asking the same thing. So you say that Scala and Haskell has evolved. How is this possible if the derivation is strict, or in lack of better words?
The reason it's possible is because each evolution step is designed to be consistent with the original semantics.
Yeah. Okay. Right.
As much as possible.
Yeah.
You know, right, and that's why you have, like, on the Scala, on the Haskell compiler, you have a lot of flags, right?
Mm-hmm.
So you can say, with overlapping instances, and
right. Yeah.
and right. So that's why. So the reality in the Haskell's case is that there's not one language.
Mm-hmm.
There are like more than half a dozen languages, each with a slightly different semantics.
Yeah, and
right.
you can combine them so you get combinations as well.
Correct, exactly right. Cool, so hopefully that covers that. Was there any other question along this? Okay, cool. All right, so to get to the abstract machine from the calculus, Oliver Donvie and company have shown a really powerful method to derive the abstract machine. And I can... so there are a series of papers that began around 2005 to describe this method, and they've really taken it quite far to the point where it's a fairly robust method, and the nice thing is that it's monadically structured. So as you add more semantics to the language, that is what you get is a kind of mix and match of the monads that are present in the abstract machine, and that's actually, I mean, I don't have time in this sort of discussion to go through the details, but that actually turns out to be a really a lovely construction, and very practical in terms of structuring the semantics of the abstract machine. Likewise, to get the VM out of the AM, it's largely a matter of creating opcodes for each step in the abstract machine, and then you have a compiler which is taking you, which is producing the bytecodes, which the VM then executes. So, and that, for whatever reason, that bytecode trick still turns out to be an enormous performance win for most sort of abstract machines. So that's really sort of the nature of the VM, at least as viewed from this perspective on modern runtime. Now, with respect to the surface language, there's a little bit more art to this, because programmers need a surface language that matches their intuition. Here, I would argue very strongly that the rise of reactive programming and the enormous adoption of systems like LINQ, Spark, Storm, Slick, etc., demonstrate that the monadic structuring of the surface language strongly matches programmer intuition. So effectively, if you can express it as a kind of polymorphic select from where, then you're golden. and there's nothing to create doubt that the vast majority of Ethereum concepts fit entirely within that monadic structuring technique. So that's my that's kind of the little caveat here. That the surface language itself, it has to meet with human beings, and human beings, you have to support their intuitions as much as present them with a model of the core computation. So it's a give and take at this side. So the question is, what would this look like for Ethereum plus Casper? And I have argued, over the last several months, that the domain calculus is best represented as a mobile process calculus, because essentially that's the only notion of computation that supports all of the concurrency and decentralization constraints. Of course, there are a lot of those, and so the question is, which one? Right? Pi calculus, joint calculus, ambient calculus. My argument has been, or has now taken, I've taken kind of a bold step, which is to say that a reflective form of higher order calculus is best. And I argue this in terms of the features of that are emerging in terms of Ethereum plus Casper. So what we're looking for is a compositional account of consensus. So I argued at DevCon that in order to scale, you need a kind of nested notion of consensus, and a corresponding nested notion of the state of the blockchain. So you have consensus on some chunks of the state, and you have consensus on other chunks of the state, and those two processes can and should as often as possible run independently, unless you have some kind of contract or computation that needs coordination amongst them. And then the question is, how do you organize that coordination? So that's one piece of the puzzle. And then the other piece of the puzzle is metering and monitoring of execution and storage. So what I'll argue is that both of these make essential use of a reflective higher order version of the Pi calculus, which I dubbed in 2004, 2005 timeframe the Rho calculus. So I can present this in exactly one slide. The important thing is that the simplicity of the calculus belies its power, just like lambda calculus. And simplicity is good because when we're talking about systems like this, they are really, really complicated. So the syntax is different from the Pi calculus, you'll notice, because there's no new construction. It turns out that you can, if you read my original Rho paper, you can compile new into this calculus in a way that faithfully preserves the semantics. This is different from Sangiorgi's higher order Pi calculus because we don't have to have separate variables for passing processes around. And the key trick is that the names are actually codes of processes. So there's an extra grammatical production, which I've not here, but here it's this X, Y, Z, whatever is. I usually these days I've been using at of P. So you have the at star combo, which kind of matches the C reference of and D reference operators, and those are a fairly good analogies to what's going on. A name can be seen as a way to get back to a process if you ever needed it, and then and because that is the case, you can dereference a name to get that process and start running it. So then the grammar for processes says, okay, a process is either the stopped process, input blocked process, a process that will asynchronously do an output, And here the output is actually a process. What will be sent is the code of that process. Now, if you think about it, that's very much what matches execution in today's web, right? When you a lot of applications end up shipping code. You don't. Very few of them take a running process, serialize it, package it up, and ship it somewhere else. Rather, what you end up doing is, and even serialization can be viewed as taking the code of something, but now you're taking the code of something plus its execution environment. So anyway, so this idea kind of very much matches how execution works in the web today. The star X is dereferencing X. So you go from the name back to the code that it represents, back to the process that code represents, and then finally you have parallel composition of P and Q. Now, in the original row papers, I point out that a proper factoring of the pi calculus abstracts over the match rule, and so what you say is if you have this, an input guarded process that's waiting on X underscore T, and you have an output process that's outputting at X underscore S, then in order for these two to affect a channel whereby this data gets supplied to this function, then what you need is some predicate that says that these two match in some way. And when they do match, then the data is sent along the channel, and you essentially apply the function, which is to substitute in the body of the process P the code of Q for every instance of Y. And so this abstraction in the match predicate turns out to be incredibly powerful. So to recover the sort of basic row calculus and or the pi calculus, you just set the match predicate to be name equality, whatever that is. But it turns out that you can do much fancier things. So since we know that X underscore T and X underscore S are the codes of processes, one of the things that we can do is we can say, well, let's say that at R is X underscore T and at S is X underscore S. Then what would happen? Well, we imagine that whenever you run R and S in parallel, for any T that it reaches in some number of steps, that T eventually goes to 0. And what this predicate says is that all paths, all execution paths leading out of R in parallel with S go to 0. That's the import of this particular logical specification of the match predicate. So R and S essentially annihilate each other; they eat each other up. So in terms of physics, you can think of this as kind of the particle and the antiparticle, and they eventually go to 0. Now,
just a clarification: what is star T in this case?
So it's not star T, it's any number of steps. So it's arrow stored. Yeah, cool. Hey, good to see that you're here. I didn't notice that you joined, Aaron. Glad to have you on board.
Yeah, confused me.
Yeah, no, totally understood. I should have sent out a note last night. Okay, so anyone who's paying attention here might get uncomfortable. Right, because they say, hey, wait a minute, your match predicate is now utilizing the arrow that it's defining. So how does that work? Does that actually get off the ground? Is that recursion well-founded? And it turns out that if you check it for the base case where you have the code of the process 0 and the code of the process 0. Well, 0 in parallel with 0 after 0 steps becomes 0. And that certainly implies that all paths out of 0 after any number of steps goes to 0. So 0 is its own code channel. And it turns out that once you have 0 as a code channel of itself, then you can build an infinite number of other channel-code-channel pairs. So here's an example of one that you can test for yourself. If you take the name of the process that's waiting on the 0 for anything and then will become 0, and you run that in parallel, the name of that process is co-channel with the name of the process that outputs on 0, 0. So that also satisfies the annihilation property, and again, you can just keep going like this. So basically what you do is you just build up processes that sort of match every output with an input and every input with an output. So there's a kind of linearity that's happening in the annihilation process, and that linearity is what's key there. And so that allows you to ground out or show that the recursion is well founded, and it turns out that there are a lot of tricks that you can do with this, right? So it's not necessarily the case that you have to go to 0. You can go to some state S, and as long as S has certain kinds of properties, then this can ground out. And that's the basis for the next point. So compositional consensus takes the reflective COM rule a step further. So synchronization is affected by consensus, which is described. So this is the really cool bit, which is described by processes that communicate and synchronize by consensus, which is described by processes that communicate and synchronize by consensus, right? So you get this reflective tower, so in particular, what we're saying here is that this match predicate is really running a kind of Casper betting cycle, and that the Casper betting cycle has some good properties with respect to grounding out the recursion, and now we are free to write the Casper betting cycle in the very calculus which is depending upon that as its synchronization step. So that's the compositional trick that's necessary to provide a compact specification of a kind of compositional or nested Casper. So that's and some of this is just a little bit more detail about how that works, but that's kind of not important at this level, and you're free to read those notes and ask me as many questions as you want. So how does this fit with sharding? So let's think about a system, say Z, that is a composition of M shards. So each shard is going to be a big parallel composition of a bunch of validators, right? So big pi V1 is like down here, right? You've got V11, V12, etc., right? And those are all validators that are all talking to each other, and they're talking to each other using the Casper betting cycle. Likewise, out here at the mth shard, which is VM, an unfortunate collision with VM in the sense of virtual machine. My apologies. You've got another collection of validators that are all talking amongst themselves, and then Z is the big parallel composition of all of those. And then each of these validators is maintaining a chunk of the blockchain state, right? So B1 through BM are the pieces of the blockchain state that they are maintaining. And now this, so that gives you a kind of, how do I write down systems like this? Well, this is the style of the expression, right? And that fits entirely within the calculus, right? There's our calculus syntax, and this is an expression in the syntax. And now, how does this fit with typing? So in the past, like a year ago, I wrote this paper, Linear Types Can Change the Blockchain. And now I'll show that that this actually fits and fits with the whole type checking sort of approach. So each validator is really a parallel composition of its subcomponents, right? So there's a piece of the validator that's handling the betting, there's a piece of the validator that's handling block publication, and so on. And there's a piece of the validator that represents for the validator its understanding of the blockchain state. Right, so that's a kind of decomposition of what V looks like. So each of these shards is maintaining a picture. That picture has a corresponding linear type following the methodology of the linear types can change the blockchain. And then to get the picture of the entire system, you have basically just the big tensor composition of each of the linear types of each of the shards. So this is how you get the total picture. And what we're saying is that the big parallel composition of the little parallel compositions of each of the validator chunks has to satisfy the linear type of the entire system. So what that means is this is actually going to describe sort of legal transitions across the entire blockchain state. And this big parallel composition of validator chunks are going to have to satisfy the constraints on the entire blockchain state. And yet, none of them necessarily knew about each other or knew about these kinds of typing constraints. They were designed autonomously, they execute autonomously, but we can still get a global end-to-end picture of what correctness looks like. So to me, that's incredibly powerful. It fits with the development methodology. So notice that this was really just a sanity check. If we make this assertion that a compositional account of consensus looks like this, does it map onto our picture of the architecture? Yes, it does. Map onto our picture of sharding? Yes, it does. Does it map onto our picture of how types are going to constrain that execution? Yes, it does. Now, notice also that Casper, that we make essential use of reflection, right? It is hard to imagine how to do this trick without reflection. So this particular approach, just for the nested consensus, is making sort of essential or fundamental use of reflection, giving credence to our argument that of the variety of calculi that might occupy this spot, the row calculus seems like a very good candidate. Now, if we go further, let's take a look at metering. So I presented this argument at DevCon, so I didn't spend too much time on it, but I've made the notes on this available for some time now, so people can read those. I've simply included them here for completeness. But the basic idea is that you've got a channel for the exchange of resources, a channel that represents the resource, and a channel for receiving computational steps. And then when you get enough of a resource, you can make a computational step. The critical point of all of this is that receiving a computational step is actually receiving the code of a process. So that's the essential use of the reflective feature of the row calculus for this encoding. The other thing that's kind of important is notice that I can begin with a calculus that appears to have no metering whatsoever, and I end up with a metered version of whatever process that you hand me. So there's the encoding, and we get a correctness theorem, and the theorem is that in the presence of enough of the sort of metered resource, whatever it is we're using to limit computation, if you have enough of it, then the metered version is bisimilar to, or weakly bisimilar to the original version. And that's kind of important because I don't think that exists for the Ethereum virtual machine in Ethereum 1.0. A theorem that says the code which doesn't mention gas runs exactly the same as or is bisimulated by the execution of the virtual machine. So even that basic notion of correctness, I don't think that's been proven for the Ethereum virtual machine. If it has, I'd love to see the proof. But the proof here is really quite straightforward. And so already we're beginning to see some dividends. The biggest dividend of all, of course, is implicit in these equations, which is that metering doesn't have to be a part of the VM. I've completely gotten rid of any. I don't need it. I'm encoding it directly in the calculus. I don't have to have a VM. For me, the VM is largely represented by this rule here. I don't need to modify the VM to be smart about metering. It can be completely agnostic about metering and the price of phlogiston or gas or whatever it is. And I think that simplifies the architecture considerably. And again, I've given kind of a formal argument about that, right? I've made it as crisp and clear as I possibly can. It's basically 2 pages of argumentation. So again, the summary, the moral of the story then is that we need the row calculus features of reflection are used essentially both in the metering and in the compositional account of consensus. So what remains is what would a row calculus inspired contract language look like. Again, I've argued fairly explicitly that this is a little bit of an art. You know, it's not like using the Don V method or just producing by opcodes for the transitions in the abstract machine. Those are all completely mindless, and you know, you could take Peter Sewell's OT, which is a system for kind of describing these things, and you could use OT as the basis for completely automating this part of the pipeline. But this part here is still a bit of art, and that's because you're meeting with human beings. And hello, say again. Okay, all right.
Sorry, that wasn't me though.
Okay, all right, no worries. I sent around some notes, draft notes about a contract language that's based on this. And I just wanted to, you know, give a tiny little example of what it would be like to program in a language based on that calculus. So here's a simple contract for getting and setting a cell. So basically, it's like a proto wallet. So it's a process that is parametric in a channel get, a channel set, and a channel state. And the idea is that you select on a couple of different possible message flows. The first of those, and so one of these cases will run and the other will not. So let's say that a get message comes in, or a message comes in on the get channel. So that we use kind of monadic notation here. So off of the get channel, we get a return address where we're going to return a value. And likewise, off of the state channel, which is where we store the state, we get the value. So if we're able to get these before we get these, then what we'll do is on the return channel, we'll send V, which is the value that's in the state channel, and we'll republish V back to the state channel, and then we'll run the cell again. So that's kind of a very simple-minded way of doing that. Likewise, if we get the set first, so we get the new value off the set channel, and we get the value that's stored in the state. So we update the state with the new value, and we recurse, you know, instantiating the cell. We recursively, you know, invoke the cell again. So that's the and so you can see that that's safe. It will safely execute a stream of gets and sets. And so it kind of implements a very, you know, simple-minded notion of a wallet. Looks like I didn't update these, but I can go to here and give you the last couple of pages. This is still very much under construction. So there's that. Here's a slightly more detailed look at the syntax that I've been proposing. It's in the notes. I just wanted you to see that there's a broader, there's more fleshed out than just a few examples. And the other point is, again, in favor of reflection. If you use a reflective calculus, then that allows you to make values as first-class processes, which allows you to kind of directly import all of this, the standard data types. It gives you an easy way to do built-in types. So string, int, float, Boolean, yada yada yada. All of the date time is another good example. All of those kind of built-in data types have a natural embedding. It's really hard. It's a tricky, fussy design decision how you represent built-in data types in the PyCalculus. There are a few different approaches, and they all have trade-offs. When you do it reflectively, so that values can kind of be first-class processes that you can ship around, then it matches almost perfectly with programmer intuition for the way they handled values in modern programming languages today. And it turns out, I mean, I don't know if you guys are aware of this, but so I did Rosette. Let's see. With Christine Tomlinson, Mark Scavell, and a bunch of other world-class researchers at MCC. Rosette was a fully reflective actor-based language that we utilize to do things like ATM network management system for TSB in England and Sumitomo in Japan. We used it to do data cleaning for Bellcore, data cleaning for Eastman Chemical Kodak. Anyway, so it was put under a fairly significant pressure in terms of industrial scale applications. Here's the actual implementation of Rosette. You're more than welcome to go and look at that. We had a bytecode VM. This was in the late 80s. But the reason I bring it up is because this also follows the architecture that I was talking about, and at the same time it does that reflective trick with built-in types. So built-in types are treated as first-class actors. So you can walk up to an integer and say, "What's your mailbox? What's your meta?" And those will be handed to you. And so if you, for example, if you look here at the implementation of the VM, you'll see exactly how that is handled. Should you be interested in that level of detail. So the point is, I'm not just talking abstractly here. I'm talking about stuff that goes all the way to high performance code that's been used in industry. Okay, that's my story, and I'm sticking to it. Sorry to ramble on like this, but hopefully that was useful. Any other updates from anyone else? Hello?
Hey. No, I just have a question. Where you said you posted the notes of the
yeah, I posted them in the Casper research. I can post them again. I'll just post them now. Hang on a second. Oops, not that one. Okay, not that one. That's weird. Oh, wow. Okay, where are they? Oh, there it is. Okay. Yeah, so there's contracts for scaling, which is some draft notes on the surface language. And I'm going to put that in Slack right now. Okay, so that's posted. There's the notes that I've been talking through today. Hang on a second. and that's posted. And then if you're interested in the Rosette VM and the repo, that's posted.
All right. I got the first two. That third
Okay,
one's
cool.
probably above my pay grade.
No worries. And if people are interested in the details of the row calculus, I can provide that reference as well. So probably the best paper is well, I'll give you both. So here's one. That was the original paper, and then the one that includes a behavioral type system is the one about the namespace logic. The namespace logic is so powerful that you can define a a firewall statically. So you can say, you know, this process will never respond to messages on this range of channels, and will only respond to, you know, messages on this other range of channels. So that gives you some sense of you know, what's going on when you have the reflective capability. Then you can look inside the structure of the namespaces. And that's part of the reason why I have been so strongly in favor of sharding by namespace. So the namespaces really do have internal structure, and once you realize that, then there are all kinds of typing tricks you can do, but also gives you new kinds of cryptographic security. Because, you know, once the names are not just, you know, addresses in SHA space, then you can do, in other words, they're unbounded potentially in terms of size. Then you can do all kinds of algorithmic specifications of namespaces, and that becomes a new layer or level of security. Okay, any other questions or thoughts?
Do you have a more fleshed out version of the Casper com rule presentation?
Not written down. That's my next step. Actually, well, the step before that is I'm really focused on getting a formal proof of convergence. Now that I've got we've got a couple of proof sketches laid out, it's time to, you know, really provide you know, formal proofs of the convergence of the betting cycle.
Yeah. I have a slightly more involved question. Maybe others will want to provide their updates first, but otherwise I can pose it.
Did we lose Vitalik?
Yeah, I think so.
Okay. Oh well. Sure. If anyone else wants to give an update, feel free.
Okay, so anyway, in the Casper match predicate, you're basically saying that a channel can be formed if the two names, if their processes form a betting cycle, right?
Yeah. To be really technically accurate, what I'm and Vlad and I went over this on Friday. The channel forms if you have a finalized betting cycle on a, you know, on some state, which, you know, for simplicity purposes we can say is a block at a height. Right. So when you finalize the block at a height, then a channel forms and you can have data flowing.
Mm. So, but this is all from the names that they communicate over, right?
Correct. Yes.
So, does this mean that the validators are communicating using names that are their own quotes?
No. That's a great question, but they'll be using names that map to code that implements the betting cycle at level n, right? And then the processes that implement the betting cycle at level n will use names that implement a betting cycle at level n-1.
Right.
And,
okay.
right,
Yeah.
so it keeps descending, and you can show that the names descend to they ground out. There's a bottom level. At least in the grammar that I showed you, names cannot be non-well-founded, right? In other words, as there's always, as you descend and descend and descend, you always get to 0 at some point.
Yeah. Okay. Great.
Cool. You might be interested. I showed that there are that you get a lot of expressive power. That there's an analogy to the Galois extensions, where you can add fixed points to the namespace. So you can write down a recursive equation like a name is equal to some process that involves that name. Sorry. To be more precise, a name is equal to a process, the name of a process that involves that name. And then you can show that you can build towers of row calculi where you keep extending the namespace to add the fixed points. And the final, the completion, the end of that recursive process of extension is a row calculus in which you include recursive specifications of names. So that's kind of like the relationship between the constructible numbers and the rational numbers. So the constructible numbers are, sort of the set of all constructible numbers is like the version of the row calculus in which you've added all of the recursive specs of names. And so that turns out to be a very powerful method for providing a semantics of new. So essentially, when we looked at how to map the pi calculus onto the row calculus, we looked at 3 different strategies. Strategy number 1 is you have a centralized global names service. That's the most obvious one. Right, so every semantics has to take the global name service as a parameter, so that there's another one which I provided in the original paper where I show that you don't have to have a centralized name service. So that works. Just read the paper on that. It's a compile time strategy rather than a runtime strategy.
Yeah, I read it briefly.
Yeah. And then the final one, which is really slick. I mean, I don't think I would. I mean, I don't know that I wouldn't do this, but my intuition would lead me away from this approach, practically speaking. But from a mathematical perspective, it's quite cool. You can implement new in terms of these fixed points. So if you don't initially include the fixed points, right, then you've got an infinite number of these fixed points, right? So you can whenever someone says new, you just reach for a fixed point that isn't in the set of fixed points that you've so far added to your namespace, and so that gives you another approach, which is again decentralized. So it's a kind of cool trick for implementing new. It also it gives some insight into how grammar extensions are like Galois extensions.
Oh, like what? Sorry.
Galois extensions. Where you take a root of a field that isn't in the field, and you just adjoin it to the field, and you complete the field with all of the by forcing all the formal expressions and then making sure and modding out by all the equations that the field must satisfy.
I think
All
you
right.
have to read more about field theory to properly understand it.
Yeah, so maybe Aaron would understand what I'm talking about there. Cool. Well, I really appreciate everybody's questions, and if there are any other questions, feel free. Again, my part of my aim in this work, to just make it clear, is I'm trying to surround Casper on all sides by sort of practical considerations that pin it down as much as possible. So I think that Vitalik has been working very much at sort of the core. How do we get a particular strategy to converge? And I think that's really important work. I've been trying to make sure that I have a sense of how Casper fits into a larger scalable architecture that maps onto modern runtime in a practical way, and make sure that at every point where Casper makes contact with that world, it's as nailed down as we possibly can make it, so that whatever we build is kind of practical in that sense, and not just in the sense of an individual strategy. So that's how it relates to the Casper research in general. Awesome. Well, is this time workable for folks until Europe catches up with the daylight savings time shift?
I'm fine.
Yeah, that'll be like in a week anyway. So.
Okay, cool. Hudson, thanks for joining us today.
Yeah, thanks
No
for
problem. Yeah, I just like listening in on this kind of stuff and trying to learn through osmosis.
Sweet. Yeah, absolutely. Okay. See you again next week at the same time.
Yep. Bye for now.
All right. Ciao, ciao.